very happy to introduce the first of this morning's talks, which is Anton Alekseev, who will be talking about the multiple Horn problem.
Yeah, thank you very much. My great thanks to the organizers for giving me an opportunity to speak here. And of course, the main thanks are to Lisa, Jonathan, and Yael for having been born some time ago, not so long time ago, and kind of being here for us. And great thanks being here for me for all those years, for great inspiration and for encouragement. And I hope I will have also other opportunities during this week to say maybe more personal words to each one of you, and I have many of them. Right, now back to mass. I was just instructed by Sue that even though it's a birthday conference, but it's primarily a mass conference, so let's do some mass. The title is Multiple Horn Problems, but I will spend probably most of the time recalling you the ordinary or classical horn problem, what it is about. It will come in several versions. The first one, let me call it additive. That's the classical horn problem, properly speaking. So we start with a pair of Hermitian n by n matrices, and everywhere there will be that letter n, which corresponds either to the size of a matrix or maybe to some other parameter in the problem. And we fix eigenvalues of those matrices. So I will denote them by lambda 1 and lambda 2. And in principle, it would be better to choose some different letters, but I blame it on the Greeks. They didn't invent enough letters which obviously correspond to eigenvalues, and I need at least 3, lambda, mu, and nu. So let's order them in, say, decreasing order. So there are n real eigenvalues for each of them. And the Horn problem is to determine the possible eigenvalues of the sum of those two matrices. And those we're going to call mu's, again, in the decreasing order. So this is a classical and difficult problem of linear algebra. Horn formulated a conjecture, and this conjecture was proved by Klatchko and Allen Knudsen in the joint work with Tau. Since then, there were many proofs, so there are many proofs of the conjecture in the literature. Maybe later on I will touch upon some of those proofs. But maybe now, instead, let's look at other versions of the problem. And for us, it will be important that actually there are several versions which are, well, let me first state them, and then I will tell you about the relations, interrelations between them. So one of them is as follows. Now, instead of Hermitian matrices, you are taking elements in GLNC, or you can actually take elements in GLNR. So these are two matrices, A and B, and their product. And instead of eigenvalues, one is looking at what is called singular values. That's something which is popular in numerical analysis. And these are just eigenvalues of the products A star, BB star, and then it will be AB times AB star. They are, of course, also reals, but now positive reals. And let me denote them with the exponential parametrization. So I will be suggestively using the same notation, small lambdas or small mu's, But I will take the exponential function. Of course, that's just a method to how to express it. I'm just using this notation for positive reals. And here, similar. So again, the question is the same. Suppose we know singular values of A and singular values of B. What are the possible singular values of the product, A times B? So the problem is always the same. So the third version, let me call it planar networks, or sometimes we're going to be using the word tropical, and it will be explained later on. So here it will take perhaps a little bit more time to explain what it is about. So first of all, let me recall that planar networks, these are planar graphs which are located between, let's say, two vertical lines on a plane. So this is the vertical line L, and that's the vertical line R. And so we place n sources on L and n sinks on R. And we have an oriented graph, plane oriented graph in between, where all the edges, they go from left to right. Let me give an example, and this example will serve us later on. So that's a particular example, but you can basically place here whatever you want, but all the directions are like this. So it should have a positive projection on the horizontal axis. And we place weights, which are, to simplify things, let's say that the weights are real numbers. We assign weights to edges. So we have a graph oriented, and to each edge we associate a number. Now to this construction, we're going to associate again something that we're going to call eigenvalues of that network, even though it's not fully justified, but by analogy with what happens on the other boards. So in particular, lambda 1, this will be a maximum over paths which go from L to R. For instance, let me try to draw an example of a path. So this is something which starts on one of the sources, then go along the edges with the orientation preserved, and then end on one of the sinks on the right. So this is a path.
Can it also go up or just down?
Sure, it can go up or down. Like here, it cannot quite go up because I didn't draw the edges.
But in principle, you would allow it. Thank you.
Okay. So, and here this would be the sum of the weights of the edges which belong to that path. Now it gets slightly more involved for other eigenvalues. So let me give you a formula for lambda 1 plus lambda 2. And this is a max of a gamma from going to L to R, which is a so-called two path. And here formula is the same. So the sum of weights. And a two path is just a pair of paths which don't touch. Now you see I added, I don't know what about colors, I added to the blue path a green path. Do you see them? So now this collection is a two paths. They don't have common vertices, they don't have common edges, they don't touch. So I consider all such pairs and I take a max. And so on. It's clear that the maximum that I would get, these are n paths, because I have only n sources and n sinks, and if I consider n plus 1 paths, they would have to meet somewhere, and this is forbidden. Right. Now, so there is something which replaces the sum or product, and I can take two networks, and I can simply identify R of the first one with L of the second one. Right, so here, so this is some kind of composition or concatenation of networks horizontally, and this is a new network. So, and again, the question is, what are the possibilities? What's the range of mu's if lambda 1 and lambda 2 are given? So it's exactly a similar setup than we had before. Last but not least, there is a quantum version of that problem. Let's say we have V lambda 1 and V lambda 2 E reps of UN with dominant weights, with highest weights lambda 1 and lambda 2, and you may be interested in the decomposition of this tensor product into irreducible components. So these are little Richardson coefficients, and you may be wondering for which mu's those coefficients are non-zero if lambda 1 and lambda 2 are given. So of course, before lambdas and mu's, they were antiples of real numbers. Now these are antiples of integers. So, but we have now 4 versions of the question to determine what's the possible range of mu's and if lambda 1 and lambda 2 are given. Now it is quite extraordinary that basically all these questions, they have the same answer. Of course, there are like some small details like reals versus integers in quantum and classical problems. And in the problem with planar networks, I didn't tell you what the planar network is. And if you choose a very small planar network, then perhaps you can alter the answer to your problem. For instance, I didn't say what to do if the parts just do not exist, right? Suppose I take empty networks, something like that. So for that one should make some small amendments in the network problem. But in principle, they all have the same answer. And there are several different versions how to express that answer, but I will present it in a beautiful form. One of the beautiful forms proposed by Knudsen and Tao, and this is this hive model. I prepared some small piece of material on that hidden board, and this is the n equal to 3 example. So we are looking at the n equal to 3 example, and so what they suggest to do is the following. So here we're going to say that so the additive problem or any whatever additive, multiplicative, planar network or quantum problem, they admit a solution. In other words, we have eligible mu's for given lambda 1 and lambda 2 if we do the following thing. So first of all, there is one equality. The trace equality that one needs to check, say in the case of the additive problem, we know that the trace of AB is trace of A plus trace of B. And this of course means, right, that the sum of mu's should be equal to sum of lambda 1's plus the sum of lambda 2's, right? So that's the equality that should be verified. And then there is a number of inequalities. So let me call them rhombi inequalities. And those are constructed as follows. So you draw that picture, the hive, a triangle with this network of small triangles. And you write those expressions constructed from lambdas and mu on the edges, in the vertices on the edges of the triangle. So you see here, you see the algorithm, lambda 1, 1, lambda 1, 1 plus lambda 1, 2. And actually it goes well with what we were doing with networks, right? That's a natural combination. It goes up to the sum of lambda 1's, and then you continue along the next edge, the sum of lambda 1s plus lambda 2, 1, and so on, up to the sum of lambda 1s and lambda 2s. And on the upper edge, you do the same with mu's. Since the sum of lambdas is equal to the sum of mu's, then at the top right corner, the values agree. So now you know what to write on the edges of the triangle, and then the claim is as follows. The mu's are good if you can find the filling of all the nodes in the middle, of all the vertices in the middle. Here in my example, there is only one. So you need to write some letter x there. This letter x should satisfy the following condition. So in this big triangle, there are all kinds of rhombi. Let me color some of them, right? There are more, but okay, for instance, there are those rhombi. And for each rhombus, you do the following. So let's say, is there an echo? So that's our rhombus, and we have numbers a, b, c, and d at the vertices, and then we require that b plus d is greater or equal than a plus c. So that's an interesting and surprising recipe. So if such an x exists, right, you would need to choose that x to satisfy all the rhombus inequalities, and if it exists, then this mu is eligible. And if does not exist, then mu is not eligible. So that's the Knudsen-Tau, one of the Knudsen-Tau forms of the answer. All right. So maybe now still about this classical setup. Perhaps I would like to make one important remark. So as I said, all these problems, they have the same solution. And here it is. So that's the answer. So the equivalence of some of these problems, some of them are easier, some of them are more difficult. And the original solution, the proof of that statement, at least maybe Alan would have a different opinion. I think it's a difficult one, whatever. It's an involved one. So, and it's a great theorem. No, I'm not sure because like people reproved a lot the Pythagoras theorem. Do you think they didn't like it? Yeah. Well, so let me make one remark. In fact, so the multiplicative problem, if you want, you can actually interpret it as a family of problems. So I can place here, maybe let's to simplify things. I can place here a positive real number. And of course, since we know that this problem is equivalent to that problem, the additive one, and in the additive problem, everything is clearly invariant under multiplying by a non-vanishing real number, right? So it doesn't change anything, right? The solution remains the same. So there is no harm in introducing a parameter. At the same time, it is reasonably easy to show that if you consider the limit of s going to 0, then you will establish a relation between the multiplicative and additive problem. So this multiplication of matrices, it will become very close to addition if you try to scale the eigenvalues down such that they become very close to 1. So actually that problem will degenerate to the additive problem. It is maybe more difficult, but one can give arguments which would convince us that actually if you send s to infinity, if you consider those matrices with very, very big eigenvalues, very far from 1 in either kind of direction of infinity or direction of 0, one can establish a relation to that planar network problem. So in some way, one can say that one way or another, the problem number 1 and the problem number 3 are some kind of limit cases of the problem number 2. Even though we know they all have the same solution, but it's going to serve us in what follows. Now, the quantum problem is, again, a lot more tricky. And even though it served as a motivation for what follows, I'm not going to consider it later on in the multiple case. So, but we'll be considering a version of this 1, 2, and 3 in a little bit different setup. So, any questions so far? So if not, we dive into multiple horn. I should say that the motivation from it comes from a question coming from quantum information theory. I cannot say that I understand it very well, but it's Matthias Christandl who posed us that question. Maybe later on I will say couple of words at least about what I understand. That's probably related to a version of the quantum problem. That first one is doing a training with the problems from 1 to 3. And in the additive case, let me state it, we are now given a triple of Hermitian matrices. We fix their eigenvalues. So these are lambda 1, lambda 2, lambda 3, again, those antiples. Well, now we consider the following combinations. A plus B and B plus C. So they have eigenvalues mu1 and mu2. And we consider the sum A plus B plus C with eigenvalues nu. So in total now there are 6 matrices and 6 sets of eigenvalues. And the question is again the same. Suppose you're fixing those ones, what are the eligible values of the other 3? Or you can say you just want to look for eligible values of all 6. Then you would expect to have some kind of cone, right? That's also a possibility. Now, let me formally say that we do the same in the multiplicative and planar network case, but I think I don't need to write a lot of stuff, right? You just do by analogy. Sorry? Wait. There will be a movie partially answering your question. Yeah, right. All right, so of course now you have A, B, C, A, B, B, C, and A, B, C. And well, we had a parameter, so there will be a parameter S that you can add. And for networks, it's also obvious what you do. You now got a triple of networks, and you consider each of them individually, the first 2, the second 2, or all 3 of them. So there are now, again, 3 problems as before. Sure. Yes, that's a very good question. Fortunately, it came from quantum information in that way, but you're right. It kind of, in principle, one can consider other combinations. For instance, here, like the product of A and C, or take away that one and kind of take a combination of those. Now, maybe like a wrong sort of wrongish answer to your question. In this case, at least we can say something. Of course, who knows? For the additive problem, it's probably more innocent to change because there is no preferred order. But here we do, in those two problems, we do have some order that we chose, and that order fits us well. So, yeah, I don't know like a good answer, but one answer is that here we're going to see something. So now I'm going to show you a movie which about the multiplicative problem in the case of n equal to 2. And let's say in analogy to additive problem, let me say that traces are equal to 1, or determinants traces are equal to 0, which means determinants in the multiplicative problem are equal to 1. So this means that you get, if you fix the eigenvalues of those guys, you will have more or less one eigenvalue for each of those, right? So the image that I'm looking for, that's going to be some three-dimensional body. And we're gonna now see that body.
I was going to say, the singular value question would make sense when A, B, and C are rectangular. Then
Sure.
it might be impossible to do A times C.
Yeah, but now we kind of take a safe thing. They are all just n by n, but you're right. So so this movie is a courtesy of Thomas Fraser, and it's obtained in the course of a related but somewhat different project. But well, let's see whether I can, when I succeed in running it. So right, that's now you see the picture on that screen. And wait, you don't see yet what's going on, but it will be a three-dimensional body which represents a solution of the multiplicative problem. What I want, it runs for some, whatever, 40 seconds, so you're going to have time to look at it, but maybe things to which one should pay attention. So there will be three projections of that body. So looking at those three projections, you're going to see the answer to the question of Allen, whether it's polyhedral or whether it's convex. That you're going to see for yourself. Now we're going to run a movie, S will change. And I must say, to me, that was a shock and great surprise, probably because I wasn't thinking clear enough. But before, all our experience was that all those problems were the same. The multiplicative problem does not depend on S. And now you're going to see a movie where S changes. And of course, I wouldn't be showing you a movie if the image would not be changing, right? So with S, the solution does change. Maybe I should tell you that if I were looking at a problem with 5 sets of eigenvalues, for instance, A, B, C, AB, and ABC. So this is equivalent to applying Horn twice. And that would mean that there nothing would change with S. If I would be looking at the projection like that, nothing would change. Or ABC, BC, and ABC as well. That projection is also protected. It's safe.
Because those are just two Horn problems.
Yeah. These are just a combination of two Horn problems. But that one is a kind of wrong question in a sense. So that's because, you know, if you look at that guy, so they're all moment maps for something. But A plus B, and B plus C, these are moment maps for two actions which absolutely don't commute. And that's the...
moment of that picture as well?
Sorry?
Will you also tell us the moment?
No, but they are in some way, right? Those eigenvalues, these are projections. So this is a sort of whatever.
Explicit the translation, or is this?
Maybe not now. So then maybe the last thing about the picture. You will see those bodies with some points. You see, you already see some points there. And those points, they correspond to some Doistermatt-Heckman measures that I will make more precise later. And you will see the evolution of the bodies together with their Doistermatt-Heckman measures.
Those points, those are
Yeah. But okay, now it's okay. So that's yeah. Now you see this as it starts running, right? So those curved bodies, right? They were not particularly convex, let alone polyhedral. Now S runs, and S going to increase to some significant values. And I will then, let maybe wait those 40 seconds and I will tell you what to pay attention to. You know, it's sort of interesting, right? I particularly, oh, sorry. I particularly liked, you know, the projection which was here, right? It was of some interesting shape. And also, maybe if you noticed on that projection, we also saw that all those points of this DH measure, right? It went to some branches in the image and it deserted another branch. Like, I will continue talking and I will just, yeah, I will just run it again, like, yeah, as I said, for me it was certainly like a shocking picture. I didn't expect anything like that. But of course I, like, probably by the lack of knowledge. Okay.
In the movie, there was this gray flat region where the dots weren't, that I guess you chose to draw. What's the meaning of that gray thing?
Oh, sorry. No, but okay, let maybe discuss the results and then we come back to those questions. So let me give you some theorems. So this is joint work with Arkady Berenstein, Anfisa Gurenkova, Yan Pang Lee. And I would say, to a large extent, Anfisa is our leading researcher on that part. What I'm talking about is also, like, some part of it is her master thesis. The main results are about the network problem. So the original question of Chris Tandel was about the additive problem. To be quite honest, we don't know much about it. For like n equal to 2, which is essentially some hyperbolic geometry in H3, you can, of course, completely solve that problem relatively easily. That's how Thomas Fraser was drawing that movie. Like you can just give analytic solution of it. But in general, we don't know much about it. Whereas for S infinite or for the network problem, then we have some results to start with. So here is the theorem. So let me call what was the notation that I was thinking to use. Yeah, let me call it, for shorthand notation for the network, we'll say trop. So the image of the tropical problem is contained in the set that I'm gonna call trop, and I will now describe that set. So first of all, there will be trace equalities. Of course, like the trace of A plus B should be trace of A plus trace of B, which means that sum of mu1s should be equal to sum of lambda 1s and sum of lambda 2s and so on, right? So then let's do the following, right? Alan was teaching us to draw that hive, the triangle. Now we can try to imitate it and draw another picture. Now it will be a tetrahedron. And again, right, we can put lattice points, and then we fill that tetrahedron with the planes which go parallel to the sides. So it will create a lattice inside that tetrahedron. So we're going to write, say, again, lambda 1 on one of the edges, lambda 2 on the next one, lambda 3 on the next one. Here, logically, it should be mu1. Here, logically, it should be mu2. And then that hidden edge behind, that will be nu. So now we know what to place there. And now we want to fill it in with something, right? We need to fill in again all the intermediate sides with some x's, which satisfy rhombi inequalities. Now there will be rhombi inequalities in all possible directions. There are many rhombi which live in some planes. Now they all need to be satisfied. Yeah, in the interior, everywhere, right? You can have lots of rhombi there. And there is a new interesting element. So there will be a number of elementary or small tetrahedra inside. And the small one, I call it small, if on each edge there is exactly one interior lattice point. So there are 6 of them. There are 6 edges and 6 lattice points. And let me call the corresponding numbers A, B, C, D, and E, F. So they come in 3 pairs because there are opposite edges, right? Each edge has an opposite edge. And if we denote alpha A plus B, and I'm sorry, I'm using the same letters as before, but now these are just real numbers. Beta is C plus D, and gamma is E plus F. Then this trop, it has the following tetrahedrotropical equalities, which means the following. Alpha is small or equal than max of beta and gamma. And then you make cyclic permutations and you get 3 other inequalities. Why do I call it a tropical equality? Because if you draw a graph, for instance, of beta as a function of alpha. So let's mark gamma on both axes. So then the set of values which satisfy those equations, it has this shape. And it's a piece of so-called tropical line, right? It has 3 branches. Note that this is not quite a function, right? Beta is not quite a function of alpha because there is this branch. If this branch were not present, then it would have been a function. Now, so the theorem says that the image of the tropical problem is inside that set. We don't know probably if the networks are big enough or all of this set. But that we only know for n equal to 2. If n equal to 2, we get all of it. But if n is bigger, who knows, maybe it's some subset. Maybe there are some further conditions, even though it is in some way unlikely. You mean for higher n? Not yet, not yet. But here maybe I can state a conjecture. Sorry? Inequalities?
Linear.
Well, linear depends what you call linear, right? They're piecewise linear, yeah. But in the network story, there are only piecewise linear functions. That's why, of course, you see when S is very large, when you approach that tropical limit, that's why you approach that story. Maybe I also want to say that maybe there is some analogy with yesterday's talk of Daniele. Remember, he had some parameter which was sent to 0 or to infinity, and then complicated trajectories of the Toda system, they were becoming some kind of straight lines. So I think it's probably related or similar phenomenon that we're observing here. So let me state a conjecture. So for the multiplicative problem, we believe that the image for S large enough would be contained in a sufficiently small neighborhood of that tropical set. So in other words, you know how it goes in calculus. For all epsilon bigger than 0, there is S naught such that for all S greater or equal than S naught, there would be this inclusion. And again, we know it for n equal to 2. And for higher n, for now, we don't know how to prove it, even though there is one of the proofs of the Horn problem due to Spire, which basically was doing something like that, but for the original Horn problem. And there it worked. So there, the kind of a similar question got a positive answer in smaller dimension. Here, we spent some time trying to adapt that proof, but for now, we don't know. Now, some more results. So here is a theorem. So we can impose some extra assumptions on weights of those planar networks. For many of you, probably what I write here would make sense. So this is some kind of Gelfand-Zeitlin conditions or inequalities on weights. So we impose more conditions on weights. And then in all of those small tetrahedra, one leg will disappear. So then this becomes a function. And actually, in that case, what's going to happen, you will have some two, for instance, starting from these two faces, so the down face and this face that we have here. Using the tetrahedral now equalities, you will be able to read what's going on in the whole of the tetrahedron. And that's something that people knew already for many years. So this is called octahedral recurrence in this theory of crystals. So that people knew in crystals or in quantum groups. So we read about it in Henriques Kamnitzer, but there were works before that. But they were basically looking exactly at this procedure, how you read the whole of the tetrahedron from the two faces. So it happens when you impose those conditions on the weights, but we know that in general this doesn't happen. In general, there is a third leg, and you cannot read tetrahedra in any way. Okay. So finally, about the measures. So let me sacrifice this one. So let's denote by DHS no, let me say right. Yeah. So the DH measure in the multiplicative problem obtained from the Lewinstein-Poisson structure. So you probably all know that in the additive problem, right, those conjugacy classes, Hermitian matrices with fixed eigenvalues, they're coadjoint orbits of UN. So this means there is a natural measure in that series. Very similarly, in the multiplicative problem, there is also a canonical Liouville measure associated to symplectic structures on so-called dressing orbits. So you start with a Lewinstein-Poisson structure, you induce symplectic structures, and that's how we get those points, right? So the image has a Dustermatt-Heckman measure. So then the theorem is saying that for all epsilon 1, epsilon 2, there is S naught, such that for all S greater or equal to S naught, the measure of the image S intersection with the neighborhood of trop is greater. And here, let me normalize the total measure as a probability measure. Let me say it's 1. So in the neighborhood of this trop, of that set, trop octahedron. So these are all trop without those third legs, right? So I eliminate the third legs, so this gives you a subset of trop, right? And so the measure will be all flowing to the neighborhood of that set. That also what you've seen on the movie. Let's play it one last time. And so the points, right, they will go into those 2 legs. So the beast has 3 legs, and the third leg, it is still in the image, but the measure goes away from it, right? And we'll soon see it. Yeah, I don't know why it doesn't want to stop in the end, but you see right here that we start seeing it, the measure wants to go away, and as it takes the shape, right, the points completely abandon that third leg, and they go to the other 2 legs. Okay, well, for now that's the last result, and I would like to again wish you a very happy birthday. And I would like to stop here. Thank you.